This is example 14.5 from Discovering Design with Chemistry, and now we are talking about entropy. They want us to determine the sign of the change in S for the following reaction, and we have 3 different reactions. So let's look at the first one. The most important thing is the phases, so let's check out the phases first. We have aqueous, liquid, and gas. The gas is going to have the most chaos, or the least order, and so that alone tells us that the system is going to gain entropy. But let's check on other things too. Next, let's count the molecules. So we have 2 molecules over here, and on this side we have 2 plus 1 for a total of 3 molecules, which means more chaos on this side. It gains entropy. And so again, this side's the winner, both for phases and for number of molecules. So because this one gains entropy, our change in S is going to be greater than 0. All right, let's look at the next one. Now, they do point out that we aren't considering the change in S of the surroundings, and so we don't know if it obeys the second law of thermodynamics, and which is that, I think that's the one where it's like the universe can only get more chaotic. Where is it? Yeah, the entropy of the universe can never decrease. It must always stay the same or increase. And so we don't know if it's obeying that law yet because we're not comparing it to the surroundings. We just know that this system isolated gains entropy. Okay, next one. Determine the sign of delta S for the following reaction. Let's look first at the phases. Okay, so they're all gas, so that tells us nothing. Now let's look at the number of molecules. We have 2 plus 1 on this side, and then we have 2 on this side. So the winner for molecules is here, which means there's, I guess you could think of it as there's more chaos on the left, on the reactant side. So this one is decreasing in entropy or losing entropy. And so for this one, the change in S is going to be negative because it's losing entropy. Okay, last one. Same thing. Let's start with looking at phases. We have mostly things in the aqueous phase, liquids, and then we have this one solid right here. And so the solid phase is the lowest entropy phase, which means this one's going to decrease in entropy by having that solid involved. So this side is going to have a little bit more chaos, the reactant side. We can also count the molecules to see. So we have 1 plus 2 molecules on this side, that's 3, and then 2 plus 2 molecules on this side. Oh, what on earth? Okay, just kidding. We do not have 2 plus 2 molecules on this side. This 2 is not supposed to be here. Sorry about that. We have 1 plus 2. My pen doesn't like me right now, which means we also have 3 on this side. So both sides of this equation have the same number of molecules. So the only thing that we're really going to look at is the change in phase going on. And because it went to something that has lower entropy, we're going to say that this lost entropy. And so our change in S is again going to be less than 0 because of the decrease in entropy. And that's based on the phases.